Welcome everyone. Welcome to Iron Beetle, a show where we stream interesting stuff about Tiger Beetle. Tiger Beetle is a database for financial accounting which is built using slightly unconventional engineering practices. We use deterministic simulation testing. We don't allocate memory after startup. We build everything in Zeek. We don't have dependencies and all this stuff. And frankly, if you've been with Iron Beetle for the past 50 episodes, you probably know something about it. Okay, so let's jump straight in because today we have an exciting topic to cover. As a reminder, for the past 2 or 3 episodes, we were covering the procedure of state sync. Tiger Beetle is a replicated state machine, which means that the logical state of each replica in a cluster, and there are 6 replicas in a cluster, is an append-only cryptographically hash-chained immutable log. And what replicas do is that they essentially append messages to this log, such that all replicas have consistent view of what is the log at every given point in time. Now, on top of this log, using deterministic state machine, we construct derived state. So messages in the log are financial transfers between accounts, and the derived state is the current balance of each particular account. So now consider the situation where a replica was partitioned from a cluster for a long period of time, and then it rejoins the cluster. Because only part of the log is actually kept on every replica, this type of replica wouldn't be able to restore its state normally. It wouldn't be able to restore the state by replaying the whole log, because again, we've some of the messages in the log we've irrevocably lost. So what this replica does is that it does state sync. It asks other replicas in the cluster to actually transfer the set of balances for accounts. And we've learned that it actually is pretty curious how this all happens. So in our replica, we realized that, well, actually, it is right here. We realized that because Tiger Beetle, Tiger Beetle's state on disk is a persistent, functional, immutable data structure, and because this state on disk is actually deterministic across all replicas in the cluster, you don't actually need to sync the entire state. It is enough to just sync the root pointer, and from that root pointer, you can derive and repair the rest of the state using the normal repair algorithm. And that's exactly what we are seeing on the screen right now. So if we are updating our superblock, and if we are doing this during the state sync, then our syncing state is in updating checkpoint, and then we have this checkpoint state which we received from another replica, and we just say, hey, this is the new checkpoint. So after we've updated the superblock, state sync logically is done, and this is perfect. What we haven't covered though is that the replica might actually be in the process of committing something, of executing some code when it decided to state sync. So let's go back to our commit process, like how replicas actually process prepares. This is commit dispatch. So this is this manually written asynchronous loop, which documents all steps which get into committing a particular prepare. So first of all, we need to figure out whether we actually have anything new to commit. If we have an entry in our log, which we know is committed by the cluster, but which we haven't yet applied to our local state. So that's kind of like the first state, and if we don't have this entry, then we obviously don't commit anything. If we do have this entry, then what we need to do next is we need to run the so-called prefetch path. So this entry is a bunch of transfers, and usually, if the cluster is fully loaded, it's 8,000 transfers. And to process 8,000 transfers, you gotta fetch accounts which these transfers transact against from disk. And for 8K transfers, it is 16K of accounts. And you kind of might code it naively, do this in a loop. So you take the first transfer, you load 2 accounts from disk, you update balances, you write accounts to disk, you take the next transfer, you load 2 accounts from disk, etc., etc. But this is the key insight which unlocks performance, because this entire batch of 8,000 transfers upfront, you don't actually need to do this one by one. You can actually go and in parallel load data from disk for all 8K accounts. And this is what prefetch is doing essentially, just goes and loads data for all the accounts. Then we need to set up a space for reply, and I guess we'll cover reply protocol. Oh, maybe right after this episode. So, but right now, kind of ignore it. Let's pretend this does this because it isn't the key. Well, it is kind of key, but not really. Okay, so this is yeah, and then this is actually the key part of commit protocol. Here, after we have prefetched, after we have done all the input-output work required to fetch all those 16K accounts in memory, then we go and we actually execute our transfers using our in-memory data, using our in-memory hash map. This is super, super fast. Then, after we have executed this, our favorite part, which we've spent most of the episode of Iron Beetle on, is compaction. We need to look at our data which exists in LSM3 on disk and figure out if we can compress it, which physically means that we are reading some tables from disk. We run in a sort of merge algorithm of the tables to find duplicate keys, or rather to find duplicate values, values where the key is the same, and then just deduplicating the key and writing the smaller result back. So this is compaction. This also needs some amount of input output. And then we have checkpointing stuff. If it so happened that the iteration we've just committed was at the checkpoint boundary, that is, if the iteration we've just committed requires us to update the superblock, then first of all, we write like all the auxiliary information. So again, superblock contains only the root pointer. Auxiliary information for checkpoint is first and foremost like the preset, and also like the manifest log. So we kind of like, we like write everything to disk, and then we write the superblock itself, and that's basically the entirety of commit. So synchronously check if we have anything to commit, then asynchronously prefetch data, then synchronously execute, then asynchronously run compaction, then optionally asynchronously run checkpoint. Okay, now, thinking about state sync. What could go wrong here? Well, one thing that could go wrong in the prefetch state, actually, I've lied to you. Like this commit start is not actually synchronous, because in commit start we need to figure out which prepare we need to commit next, and it could be the case that prepare is on disk in our write-ahead log on disk, and we need to fetch prepare from memory. So the first thing to go wrong would be that we are fetching prepare and prepare is corrupted on disk. Or we don't have prepare on disk. So that's kind of like one thing could go wrong. And here, I think the result would be that we'll get to this branch and break out of the loop. The second thing which could go wrong is like during prefetch. So during prefetch, we read data from disk to read the actual accounts. And if you recall, when many weeks ago, when we covered Grid API, we kind of like said that whenever you read data from disk, the contract is that TigerBeetle always returns you the data. So there is no API which either returns you a block from disk or returns an error. You always return a block. And the way this works is that if you don't have this particular block on your disk, maybe because the block is corrupted, or maybe because, well, you just stay synced and there simply isn't this block on disk. So in either of two cases, the replica is going to transparently ask for this block from the peer replica, so that to the calling code, it feels like the storage is infallible. And this thing can go wrong, because assume that we are a replica which is lagging. Then it could be the case that the local state we have, no one else in cluster has it. Everyone has moved forward. And if we try to read some data block and it is not there, like it is corrupted, or maybe we've state synced before and we've never had this block, well, we are going to indefinitely like block or wait for this block to come in. So okay, that's kind of like the second mental model. What can go wrong here? And this feels really bad, because here, like eventually we realize that we don't have this prepare, but for this case over here, like we just sit there and wait. No one tells us, hey, like there positively isn't blocks. Isn't this block in the cluster? We just sit there and wait and hope. Okay, then commit execute. Commit execute is infallible. This is like super easy, super simple. We have all our data in memory. We just apply in-memory transformation. We don't do any kind of memory allocation, so there is no way this could fail. Perfect. Now, compaction. Compaction actually is also problematic, because compaction needs to read data from disk, and it needs to write data to disk. And reading data goes through this same Grid API, which provides the guarantee that the data is always there, that you don't have to handle any kind of errors, except that, of course, if your replica's state is lying far behind the cluster, the data will never arrive. So we could also stack in commit compact. Finally, there is this checkpointing. And checkpointing only writes data to disk. Checkpointing never reads data, it only writes data. So it is infallible. You have this data in memory, you just write it. It might take some time for you to get your data on disk, but you cannot fail, you cannot hang. Okay. What do we do from here? The problem is that, okay, so imagine that we are a replica which is lagging behind, that we are trying to commit. And then we realize that, hey, actually, like, we've been waiting for a single block on disk for like 10 minutes already, and it looks like no one in the cluster actually has this block, and it looks like we are stuck. So at this point, we need to state sync. And we actually receive start to message from a primary. This start to message contains a new checkpoint. So we go and we we go and we want to write this new checkpoint into superblock, but we still might be stuck reading some data in the prefetch. So if we try to well, let's think about compaction, because compaction kind of slightly less usual case, but it's still interesting. So let's say we were actually in the progress of compaction, so we went into state machine compact. You of course didn't believe me when I said that we've never go into Java compaction ever again, right? Okay, so we go to state machine compact, that goes to forest compact. That ultimately is going to call compaction schedule bit start and then bit resume, and then we are going to call compaction dispatch enter, our favorite function of all of them in Beetle. And this is going to call compaction dispatch, and somewhere here we are going to read blocks. So somewhere here we're going to say, hey, compaction, read next block. And then we say greet, please read me this index block. And this is the callback for you. So this is our callback. We are waiting for index block to arrive. And this index block is never, ever going to arrive because no one in the cluster is having it. So, okay. That means that we somehow need to cancel this work. We somehow need to say, okay, so scratch that. I know that you're in the middle of compaction. I know that you've done a lot of work there, but tough luck. This actually is not needed at all anymore. Please take this new checkpoint and start from there. Okay, so let's look at how this exciting part works, because really, if you want to know how a system works, if you really want to find the heart of any kind of software system, then you need to look at two things. You need to look at the shutdown procedure, and you need to look at the cancellation. How a system cancels requests and how a system shutdowns. It's always unhappy path always puts into the central light all the properties of the system. And I kind of like how elegant cancellation turns out to be in Beetle. So we'll look at this again. Okay, so let's start. So we now we have motivation that we are stuck in compaction, and we kind of want to somehow clean that work up, release all our resources, etc., etc. Let's see how this actually works out. So this starts when we receive start to message. We've not start to change on start view. When we receive start to message, and then we start to message. We have um, every single checkpoint, and we are like wondering, like, okay, so we want to install this checkpoint. What do we do? So, well, first of all, we are going to look at this commit state variable, which is exactly what we use in our asynchronous commit dispatch loop to control where we are at in our commit pipeline. So if we are in the checkpoint state, so this state is checkpoint stage, this stage which needs to write some data from disk, but doesn't need to read anything from disk, then we know that this stage can actually complete. And in this case, we just let this checkpoint run to completion. Otherwise, well, we need to start sync from start sync. And this is where it happens. Actually, okay, this is interesting. I see, well, it's not a bug, but I think we could simplify this. So let's see, sync start from committing. Okay, so there is only sync, and we know that commit stage cannot actually be any one of the checkpoint. So this could go back to unreachable. Okay, yeah. Looking at the code on stream never fails to cut some smaller things. Explicitly. Okay, we'll need to write something better here, but basically, yeah. For check, prepare, and execute stages, like we can't actually observe them, because if you flip from some commit stage to execute, like immediately afterwards, you will flip to like checkpoint or compaction stage. Okay. Then if you have like checkpoint data in checkpoint super block, you know that they cannot hang, and you actually know that, hey, you like before you start syncing from them, you just better like, wait for your checkpoint to be done, because maybe you don't actually need state sync if you have a new checkpoint. Then finally, these two stages, like, you know, when we read prepare and from disk, and when we, I think, wait for some write for client replies to finish. So basically, the property of these stages is this. First of all, those stages are asynchronous. So meaning that, like, you know, we are waiting for some callback to fire sometime in the future. But also that callback cannot get stuck. That callback is not trying to read data from grid in an infallible way. So that callback is like guaranteed to fire at some point. So here we just say, okay, we are going to wait over those callbacks. So let's see. We okay, no, actually I think, okay, yeah, right. So so we say, okay, so we just need to wait until those async operations are complete. And we start the way we do this is that we set our syncing to be canceling commit, so that we remember that here actually we are canceling our commit process. So now if we go into commit dispatch, we'll see that if we want to resume our commit, but we also so we call commit dispatch when any asynchronous operation involved in commit finished, and we want to resume commit. And now we are resuming commit, but we see that actually we don't want to resume, we want to cancel. So here we resume our syncing process and go directly to cancel and grid. Okay, so let's see. Also, let's come back again to start sync from committing. Sync start from committing. Okay, so this stage is basically we just have to wait out. For other stages, we might actually need to proactively cancel outstanding work. And the way this is coded is that we also go from a canceling commit to canceling grid. So that's why, there we jump to canceling grid as well. But the key, that was for convenience. But the actual reason is here. So we see that we want to start sync, and we see that our commit process is that either prefetching or compacting, which means that likely our commit process is actually got stuck. Our commit process is waiting for some grid operation to finish. Okay, and here we do sync dispatch canceling grid, and this is where magic happens. So as we've seen before, we set our syncing to canceling grid, and now if we cancel grid, we call cancel. And this is the key to a lot of cancellation bugs in a lot of systems. And I mean, I love Rust programming language, but this also is a bug which Rust futures have. In that, in the general case, cancellation is an asynchronous process. You cannot cancel things immediately. And here is this simple intuition. So what we're thinking about is that, hey, we have some grid read, and that grid read is actually stuck because there isn't such block in storage. But alongside that stuck grid operation, there might be some other operation. So for example, grid at this point in time could be writing some block to storage. And writing a block to storage is an asynchronous operation. We do this through IO uring. So essentially, we have this block we want to write on disk. It's some region of memory, and then we kick IO uring and say, hey, dear IO uring, here is a region of memory for you, and I want to write this region of memory to storage, to disk, and I want to get notified when you are done. And while you are doing this, I'm going to continue to do something else. So this write operation is executed, and essentially kernel is accessing that region of memory, and our application is not allowed to use that region of memory for anything else. Now, you cannot just cancel that outstanding write. You either need to wait for kernel to finish with that read normally, or you need to notify your kernel. You need to say, hey, dear kernel, remember that grid write, that disk write I submitted 5 milliseconds ago? Well, actually, I no longer need it. Could you please stop writing that thing to disk? And again, the kernel might not necessarily be able to immediately cancel this operation. It might already be halfway through hardware, and kernel might just say, okay, I'm going to cancel it, but you still gotta wait until I'm no longer using this buffer of memory which you previously gave to me. So this is okay, let me actually even this, because this is really, really important. Cancellation is an asynchronous protocol where one party requests cancellation from the other party. You say, hey, please, dear counterparty, could you cancel? And then after you submit this request, you actually have to wait until that request finishes. This is like really, really important. You cannot just say, hey, like, please cancel, and like consider that the stuff is canceled. And okay, so you might say that, hey, IO Uring example is kind of like not real. Like, there are systems which don't use IO Uring, which use like ePOL, and it doesn't apply them. And it, in general, like, it's esoteric. But no, this is property of many different systems. And here is another example of why cancellation needs to be asynchronous, which is like really, really down to earth. Okay, so imagine you have an application, and your application needs to compute checksums because, well, maybe your application is a database, and, well, databases usually compute checksums. And computing checksum is like kind of slow. So you have some sort of a thread pool, like very simple, very stupid thread pool, whose only job is to compute checksums. So essentially, you submit a pointer to some byte buffer to that thread pool. That thread pool goes then and computes the checksum and like communicates the checksum back. Okay, so now how can we cancel? And imagine, like, you have like some asynchronous operation which like maybe does a bunch of like TCP, maybe does a bunch of disk writes, and also like compute some checksum. So how do you handle those? How do you cancel that asynchronous operation? Well, as a part of that asynchronous operation, you have this checksum computation. So you need to cancel this checksum. But, well, how do you cancel checksum computation? You cannot actually interrupt that other thread. What you could do is, like, if the computation hasn't started yet, well, it is canceled. Similarly, if it has finished, then it is canceled. But if it is, like, running like in the middle of a buffer, like, the CPU is like checksumming, like, you cannot interrupt that. You like have to wait until that checksum is fully checksummed. Because if you just let the thing run its course, then that buffer which holds the checksum, it's still borrowed by that background thread. So you cannot like, even if you like, why do we want to cancel things? We want to cancel things so that we can reuse the things, reuse the resources. But that resource, that byte buffer, is going to get occupied until that checksum thread is done with it. And okay, maybe, like, if you're thinking about this, you are thinking, okay, so actually computing checksum is like pretty long, and maybe I want to make it faster, so I'm not going to checksum like the entire byte buffer. I'm going to split it into chunks of like 1 kilobyte, and after 1 kilobyte of work, I'm going to check some flag and say, okay, so if someone requested a cancellation of me, then I will not continue this like checksumming work. But still, there is like, this like 1 kilobyte of data where CPU is in a very tight seamed loop and it isn't checking any flags. So moral of the story, cancellation is always asynchronous. Oh, actually, no. This is like, again, if that were true, then systems wouldn't routinely mess up cancellation. The truth is, like, in 99% of the cases, you can get by with sequential cancellation. But there is 1% of the cases where cancellation is asynchronous, and if you hit that 1%, then kind of like, yeah, you need to rewrite a lot of stuff, because like asynchronous code is fundamentally not synchronous. Okay, let's stop with our energizing speeches and go back to looking at the code. So how do we actually do cancellation? And here, I guess we'll go to review more or less the entirety of TigerBeetle. Okay, so first we look at this like grid callback state. And this is a pattern which repeats through TigerBittle. Again, like everything is asynchronous. And because there is no closures in Zeek, and because we want to have static memory allocations, we like explicitly store callbacks. And then if you store the callback, it can simultaneously play a role of, well, a callback, but it also can be a state variable which says what you are doing. So what can we be doing with grid? We could be doing nothing. So there's like no asynchronous operation with the grid. That's simple. We could be opening the grid. So what does opening the grid means? It means that, well, I need to, okay, actually, I don't understand why opening a grid is an asynchronous operation. Let me, okay, yeah, right, okay, now I understand it. Opening the grid is a asynchronous operation because we need to read the free set from disk. And again, free set is in the grid, so blocks of a free set might get corrupted. And actually, it's like it is like one of the cases where we also might get stuck in the checkpoint. So you state synced, or even you state synced, which means that you have the root pointer, but you don't have actual free set. So you go and you start reading the free set blocks, and you realize that, hey, the free set block isn't actually there because, like, for some reason or another, the cluster is ahead of you again. So you need to state sync again, and this is where like this happens. So otherwise, so yeah, you might be opening. You can't be canceling, so we don't support like recursive cancellation, and you can't be checkpointing because, if you're checkpointing, you could always wait for this to finish because checkpointing always writes data. Okay. So, well, actually, is I feel we are missing something. Or maybe not. Wait. Okay, so oh, right, because okay, so I'm confused. Let me. I'm still confused. I'm confused because I don't understand where we are canceling state machine. Let me check this state. Machine cancel. Or maybe forest. Cancel. Okay. Okay, so I'm confused. There should be cancellation. Oh, because it is called reset. Because, yeah, because synchronous cancellation we call. Okay, actually, I haven't conceptualized this this way. State machine reset. Okay. Okay. This is curious. I've learned something here. Hopefully, you will too. Okay. So, basically, I've learned that our cancellation is two-phase process. First is the asynchronous part where we stop all the synchronous work, and then this simple reset part, which says that, hey, now that you know that no asynchronous work is getting done, just reset all the resources you have to initial place. So basically, like, restore all the memory. Okay, so let's see how it works. So we cancel And okay, so this is it's actually probably should have been called just reset, because this is synchronous and we are like literally resetting the state of grid blocks missing. So I guess we need okay, so I said we need to cover okay, let's actually start writing this down, because I fear I might um, start forgetting things. So let's call it iron beetle to do txt, and here I said we want to cover client sessions and then make grid blocks missing. Okay, so now I feel better, so that you don't forget to return here. But basically, grid block missing is the set of blocks which we try to read from disk, and which we are not there on disk. So this is exactly the thing we want to repair, and we like reset it. And I guess, oh, well, I guess let's maybe maybe look at the write queue first. So kind of like as a simple pattern of like what all those resets are doing. Uh, although I don't understand why we are doing this reset here rather than at the end of the callback. Okay, so maybe I'm not understanding everything. Okay, so but basically we have like write queue. Okay, so I guess yeah, here we are resetting IOPS. So like basically like write queue is some data structure which stores in-flight writes, and when we cancel our grid, we call reset there. Yeah, and here we just kind of like restore the data structure to the pristine condition. But why aren't we losing all the writes that were there? Okay, this is curious. So let's see it. Dependent. Well, it's also FIFO is going to be the same thing, right? This is what we've looked at right now. Okay. So dependent. Read pendant is FIFO. Read global is also FIFO. Okay. So I'm slightly confused here. Yeah. So okay, it still feels correct. So basically, so the problem here is that I know what goes next, and that makes me slightly uneasy about what happens right now. So we are agreed. So as I've said, we might be issuing some syscalls to the IOU ring right now, and we really want for those syscalls to finish. We cannot just like immediately cancel it. We need for them to work. So that's why, like, what we do here is that we arrange to call this callback soon, and that calls this cancel join callback, and that waits until our read IOPS or write IOPS are at 0. So read IOPS and write IOPS store like the actual in-flight reads and writes. And if you look at read, let's see it like something like read block. How cancellation works here. So when we do read block, we somewhere go and we say, okay, we are going to read block with this read. So this read is from read IOPS. And we go storage, read sectors, and like read block callback. So now this read sectors call isn't actually cancelable. So it goes and fires up actual syscalls to the underlying IO ring, like we just wait for that to finish. And this is the key. So like normally, like when you like finish the read, you like do some checking on the result, and somewhere at the end you are going to call all the callbacks. Yeah, so like somewhere in there, like you gotta yeah, so here, so at the end, like you go and like you like call some callback when you finish the read. But if you finish the read and you realize that hey, actually, like between the moment you started the read and the moment where you're finishing the read right now, cancellation happens. Then you say, okay, we aren't going to do anything with this read. We are not going to invoke user's callback. We just going to call this cancel join callback. So the job of this cancel join callback is to actually wait for all pending asynchronous operation to finish. You see, so we call it from write callback, from read callback, from like cancel tick callback, which I don't, well, and cancel tick callback, I think we need only to prevent this thing to be like re-entered. So as a reminder, rule of thumb, whenever you have asynchronous API, which takes callbacks, which takes a callback, you either always invoke callback immediately right here, or you always invoke it later. So we need this tick to make sure that we always invoke it later. So even if right now our grid is quiescent, even if right now there are no outstanding reads or writes, we don't want to invoke a callback immediately to not overshoot our stack space. Okay, so anyway, once grid reads and grid writes go to 0, only then we go and we call back the callback saying that hey, actually your grid was cancelled. Okay, what else do we have? So this all here are simple data structures resets. Then reset next tick LSM. I guess, yeah, I guess we want the storage to like shut down this machinery for all the ticks which come from LSM. Okay, let's go to storage and see how it works. Reset next tick LSM. So we go through our next tick queue, and for every next tick which is LSM, we just drop it. Okay, yeah, that makes sense for me. Okay, so, and finally we invoke the grid cancel callback. So we go back to replica, and we call this sync grid callback. And here, like we actually assert that the grid is indeed like quiescent, that indeed there aren't any pending operations with the grid. So like that like read queue empty, write queue empty, repair queue empty, everything else that the grid is doing, it is definitely not doing here. Okay. So then we do some resetting of our own. So you see that when grid was canceling read, when grid was canceling reads, the way this works is that grid just said, okay, I'm not going to invoke the callback. So this is the compilation. This is the cancellation target. Your callback is just not getting invoked. So you aren't actually notified that you got canceled. You just not going to ping back. Instead, like a reset is invoked, and reset should restore all the resources. So replica owns some grid reads. So this is grid reads, which could have been used to read some data from a replica, which ultimately triggered the state sync. So we need to reset those reads, and we say, hey, this read, like whenever you were reading, like you're not reading this anymore, so we reset this message, and we mark this grid reads as free. Okay, then we do the same with grid writes, etc., etc. Finally, and so coming back to our example with compaction. So because remember, we like started thinking about, okay, so what happens with compaction when we cancel? We view like read, we are like in a read index block function. So we issued this grid read, and that grid read got canceled. So this read index block callback is not going to get called back. But at the same time, we do have some outstanding resources allocated here. So, in this compaction, so we get to our compaction pool and we like acquire the block and we like acquire the read and whatever. And like those things are still in use. So we have to reset them. And we get to reset them once we started updating the superblock. And now let's go through this reset workflow. So in state machine, we have reset function. And what it does is like, recursively resets everything that there is to be reset in terms of fields, and then reinitializes the data structure. So like, we reset a forest. And in forest, we reset compaction schedule. And in compaction schedule, we reset the pool. And when we reset the pool, we actually go through all the blocks and say, hey, now all the blocks are reset. So this is going back to our compaction. What was it? Read index block. So here we see that we've acquired the block, and this is the code which like resets this block back. So I'm curious, how do we reset the read here? Yeah, I guess the read it was in the pool. So I guess the read gets reset by just resetting the underlying array. So we have bunch of reads here, and they are reset. I'm wondering. Okay, so this is curious. So here we do just like this, like reset the reads, but in the replica, where was it? Yeah, we kind of like, oh, right. So the reason why we needed to release reads like this is because each read contained a message. So we actually wanted to release the messages. for these reads, they don't own any resources, so we could just like directly release them. So I guess here we could just save it like self grid repair writes equals this, and that should also be a correct thing to do. Although I'm curious, like why. Like I'm curious which one is better. So how do reads work? So we iterate over all in flight and we release it. Okay, so this is yeah, I guess this is more or less equivalent. Okay, because squid writes is block write and block write is right. Okay, so now haha, this is interesting. So this writes in the replica, they store back pointers in the replica, and we don't want to reset those. Well, okay, like this bears the question: do we have the same thing in compaction? Maybe this is buggy. So block read. Okay, so we have pointer to block, pointer to compaction, but I guess we okay. Could this be buggy? How do we initialize reads? Okay, reads we don't initialize in any way in particular. And okay, so how do we actually, well, who sets this compaction? Is it when we acquire the reads? Let's see, read index block read. Who gets your, oh, I think this is inside this. Okay, yeah. So this is so kind of like we set this at the time of use and not initially. Okay, yeah, that explains why we don't need to handle resetting the read specially. And then I think actually is like everything else that is to cancellation. So cancellation kind of like two parts. We asynchronously wait for all truly asynchronous work to finish, namely we drain all the syscalls which we've submitted to IO ring, and after that we reset all our state to be like neutral, to be as if nothing had happened. Actually, so we also have like this reset for compaction. I wonder who calls compaction reset. I guess it's like growth. Reset. Yeah, right. So this is where we reset all the individual fields. So yeah, it actually feels like pretty simple. So kind of just recursively reset everything. Okay, I guess that is a good point to end today's episodes. And this is cool because I think now we fully know how to do state sync, when to switch from repairing log to transferring the state, how to transfer a state, namely just transfer the root pointer, and then how to make sure that whenever you trigger state sync, you don't have in progress work hanging behind, which you do by implementing cancellation. That's it for today, and please join me in a week at 5 p.m. UTC on Friday, and then I guess it's perhaps going to be either like, well, yeah, let's make the next week like Christmas special episode where we'll do something surprising. And with that cliffhanger, goodbye.